Greetings and welcome to my new calculus channel once again. My name is John Gabriel, and today I'm going to speak to you about what exactly is a rate and how to teach the concept of rate to your students. So I've written a new article to which I'll place a link in the details section. But first, what does the dictionary say about a rate? It says it's a measure, quantity, or frequency, typically one measured against some other quantity or measure. Okay, so without knowing it, you've all been dealing with rates since your first grade, because a number is a rate, yes? So how is a number a rate? Well, a number compares a numerator to a denominator, doesn't it? So by comparing the numerator to the denominator, you're able to establish what the proportion is of a certain fraction, right? So for example, if you've got 3/5, that tells you that for every 3 in the numerator, you have 5 in the denominator. So it's a kind of rate, but not a proper rate as such. But I'm going to show you shortly what is a proper rate. So the concept of rate evolved from the beginning. It started off with a size compared to another size, and then it became a comparison of two homogeneous measures. Of course, these sizes also in the first place were also of the same kind. And then third, a number compared with another number. So the most primitive kind of rates are ratios of sizes or magnitudes. Now remember, a magnitude or a size is not a number. So you can have, for example, two ratios, like you see here, this ratio and this ratio. Now they are decidedly not equal. Okay, they're not equal because their antecedents are not equal. But they are in proportion because this antecedent is to this antecedent as this consequent is to this consequent, okay? So we say they're in proportion. Now, their measure, however, is equal. So the measure of these ratios is equal. Now, what does it mean when we take the measure of the ratio? Well, we say, okay, we need half of either of their consequents to measure the antecedent. Does that make sense? So we need half of this consequent to measure this antecedent, and half of this one to measure this antecedent. So ratios can only be measured if their aliquot parts have a common divisor, and this is called quotientness, okay? So for any given ratio, just this ratio by itself, it only has a measure if there is a part that goes into both the consequent and the antecedent, okay? So stop and pause the video and think about these things before you continue. Now, what about the ratio circle circumference to circle diameter? That has no measure because there is no common divisor, right? And so the ancient Greeks would say that the aliquot parts of this ratio have no quotientness. In other words, they have no common divisor or measure, okay? So any two ratios are equal if and only if their aliquot parts are equal. And I've just explained this part here to you. So this is to this as this is to this, okay? That means they're in proportion, but they're not equal, okay? Now, if all ratios have the same consequent or the same unit, then we can form numbers out of the multiples. So we can call this the unit, this by the name of 2, this by the name of 3, etc. And then the next thing we can do is form fractions from these quantities above. To form a fraction, we need to compare one ratio against another. So if we compare this one against this one, we have the fraction or the primitive fraction ratio, which is 1 to 1. Similarly, here we have 2 to 1, 2 to 1, okay, 2 to 1, and 3 to 1. So the last example is the final evolution of homogeneous rates, because here we've been dealing just with lengths. So what is being compared here? Basically, in this ratio here, wish it wouldn't highlight the whole thing. but this 1 to 1, the unit measure is compared to itself. In this ratio, the measure 2 is compared to the unit, and in this ratio, the measure 3 is compared to the measure 5. So the above rates are expressed as ratios, but we can also express these as whole numbers or fractions, and we do that by taking the measure. So we call the measure of this ratio 1, the measure of this ratio 2, and of this ratio here, this last one, we call it 3/5, right? So in these examples, we have compared only the same kind of magnitudes, all right? So multiples of the unit or 1, and that's what you typically come to understand as whole numbers when you begin to learn about arithmetic and so on. Now, the next step is to abstract the unit. That is, no longer to care about the unit size or the type. And this is of course different from the previous example, because what is being measured in the previous example are whole units. So what if you have something like egg, car, and rabbit? Then we can describe this by this ratio, 3 to 1, and its measure as 3/1 or just 3, okay? Its measure as 3/1 or just 3. And here the denominator, whose ancestor is the consequent 1, tells us we're measuring in terms of the whole abstract unit. And of course the numerator, 3, tells us how many objects are measured or counted, because guess what? To count is to measure. It's the same thing. So these ideas are equivalent to the primitive notions of set theory, which is compiled or designed with facts that they call axioms, and they do so without proof because they've never understood the concept of number. So thus far we have described, again, mostly homogeneous rates, and these rates here are no longer homogeneous. We have an egg, a car, and a rabbit. Their measure is one abstract unit in each case, and if we have a car and an egg, there are two abstract units, okay? And so on. So a rate does not need to have the same types, and most useful rates generally do not. So for example, we can have a rate, as you see in front of you here, 1 teaspoon of dye to 2 cups of flour, or for every 2 cups of flour, or 100 miles of distance or length for every 2 hours. Those are rates, okay? And we use those rates in almost every aspect of our daily lives. So we can say that a rate describes the proportion between the two different types. So what are the two different types here? Dye and flour. The one thing I hate about this recording software is that it doesn't synchronize the voice with the actual images. That's too bad. So for example, 1/2 teaspoons per cup, where T stands for teaspoon and C stands for cup. Okay, so 1/2 T/C, or T per C. And here you've got 100 miles for every 2 hours. That's 50 miles per hour, okay? So again, these are very useful rates, aren't they? So mathematics is the abstract science of measure and number, and there's nothing in any other science that we can do without number. And so here are a few examples: slope, gradient line, length, angle, derivative. All of these here, probability, etc., etc., they're all rates. Okay, so the above are just a few examples, and they're not listed in any particular order. And so as you can see, the concept of rate is derived from the very concept of number itself. So for this reason, it is essential that every student of mathematics have a profound understanding of the number concept. And teaching set theory in place of well-formed concepts, as described to you in this video, does not help students to acquire a deep understanding of number or rate. In fact, they never really actually know what is a number, because their moronic professors of mathematics and teachers have no clue what rate means. So from rate, we progress to proportion between rates. So for example, we can have two different rates. This rate of 25 milligrams per liter and 6 hours, okay? Now, by the way, time is also a rate, and you can click on this link here to see why. So you've got two different rates here, and they have a proportion. So you could say take 25 milligrams per liter every 6 hours, okay? So this kind of rate is nuanced or more subtle because it relates medicine to time, right? Milligrams per liter, which is a medicine, to time. So is there such a thing as an instantaneous rate of change? Think about that. Well, that's just a fallacy, because derivatives of functions are not rates of change. They are rates, but not rates of change. In fact, they've never changed. The slopes of the tangent lines to the function f of x is equal to x squared has not changed in past perpetuity, and not currently changing, and will remain the same indefinitely. So there's no such thing as a rate of change. That's just absurd, totally moronic, totally stupid. This ridiculous expression, rate of change, is peddled by the baboons of mainstream mathematics. So know for certain that the methods of calculus are both null and void unless a smooth function is being considered. And generally, a function is comprised of one rule or algorithm, so that the nonsensical garbage known as piecewise function is an ill-formed concept. I mean, you cannot use the same derivative or integral process on all parts of a piecewise function, because they have to be determined separately. Okay, in other words, one rule or one algorithm at a time. I hope you've enjoyed this presentation. If you're not already a subscriber, become one, spread the news to your friends, and help me out by contributing at my GoFundMe link in the details section. Remember, I am the most persecuted mathematician on the planet. It's unfair what the mainstream have done to me. And by helping me, you'll in effect be beating them. So that's pretty much all for now.